Good afternoon, everyone. I'm Rebecca Wostenberg, Research Fellow at the Emerging Technologies Institute at the National Defense Industrial Association. Thank you to all of our attendees for your support of NDIA and ETI, and thank you for joining us for today's webinar. Today's webinar is entitled Designing the Future, Tackling Challenges in 3D Heterogeneous Integrated Microelectronics for Aerospace, Government, and Defense Systems. Today's webinar is sponsored by Synopsys. Synopsys, a global leader in electronic design automation and semiconductor IP, is deeply invested in the advancement of technology for the field of microelectronics, including for the complexities of 3D heterogeneous integration. 3D-HI comes with its own set of technological manufacturing and economic challenges. Looking to the future, Synopsys is enabling chip designers to innovate, build, and deploy advanced systems that exceed mission requirements and address challenging application demands, including C5ISR, EW, security, safety, longevity, and reliability. Synopsys is supporting customers' advanced designs to develop semiconductors and ICs for extreme environments with low size, weight, and power, or SWaP, from sea to space. For those that may be new to the Emerging Technologies Institute, or ETI, we are a research organization at NDIA focused on technologies that are critical to the future of national defense. ETI performs research, hosts events, and bolsters public awareness through educational products and webinars focused on defense technology, modernization, and innovation. We also work to create a policy environment most conducive to the efficient development and delivery of new systems and technologies for the defense enterprise. Today's webinar focuses on a key component that undergirds nearly all defense systems, microelectronics. Many of the emerging technologies of the future will have highly advanced performance requirements, ranging from the need for onboard computational capability to SWaP. It's critical that the Department of Defense and the defense industrial base improve their capacity to take advantage of such cutting-edge advantages as those provided by 3D-HI, which can enable the performance improvements that these systems need at potentially more reasonable costs to programs. Some administrative remarks before we get started. Number one, all attendee lines are muted. If you have a question during the webinar, you can submit your question in the question box in the webinar panel on the right side of your screen or on the bottom of your screen. We'll do our best to get through all the questions during Q&A. We are recording today's webinar for members unable to attend and for any member who wishes to review the material at a later date. Within the coming days, we'll post the recording to YouTube for your review. Now, I'd like to introduce our moderator for today's webinar, Ian Land. Ian serves as Synopsys' Senior Director of Security, Government, and Aerospace Solutions. He has more than 25 years of semiconductor experience and has spent more than 15 years in disciplines that require security. Before joining Synopsys, he was a general manager at Intel and Altera and held aerospace and defense planning and marketing roles at Xilinx. Ian holds a bachelor's degree in mechanical engineering from UCLA, as well as a master's degree in management and mechanical engineering from MIT. Ian, the floor is yours.
Morning, can you see my screen?
Yes.
Okay, good afternoon also for those who are on the East Coast and elsewhere. One, thank you all for attending. We appreciate it. Being part of Synopsys, we are very interested in one, aerospace and defense, and two, 3D heterogeneous integration. We see a great future in those areas. I want to thank the folks who are attending with Dr. Carl McCants, Dr. Joshua Fryman, and Dr. Rob Aiken. And I'll do a quick intro of each, starting with, there we go. That would be past myself. Dr. Carl McCants, Carl has an extensive bio, so I'm going to abbreviate everything that I could say about Carl. He's a special assistant to the DARPA director, focusing on the Microelectronic Technologies Office, the MTO, Electronics Resurgence Initiative, ERI, and the National Network for Microelectronics Research and Development. Carl's, prior to his role in DARPA, he was also part of the National Counterintelligence and Security Center, and as part of the Office of the Director of National Intelligence. So pretty neat group. Before that, Carl's got a long experience helping innovation in the US government with the IARPA, Intelligence Advanced Research Project activity. Before that, he was part of the Microelectronics Technology Office at DARPA as a program manager, and had some experience in the corporate world, working for Agilent, and prior to that, Hewlett Packard. Carl has a bachelor's degree from Duke in 1981, and doctoral degrees from Stanford, and also his undergrad from, or sorry, his graduate degree from Stanford, all in electrical engineering. So quite an extensive background, and we're thrilled to have Carl. I've enjoyed working with Carl for many years now, and I'm just honored to have him. Josh Fryman, actually very similar background from Intel. He's a fellow at Intel. He received his PhD from Georgia Tech and his BS degree from the University of Florida. He's been at Intel for many years, starting at Intel Labs with the Software Solutions Group, working on virtual ISA instruction set architectures and support for what became the Xeon Phi. I actually was a big Xeon Phi fan. So, since 2012, he's led a vertically integrated applied R&D team as part of Intel's Office of the CTO, first with the data center group, and now more general with the Office of the CTO across the corporation of Intel. He has been a lead architect or a principal investigator on multiple research programs for DARPA, for IARPA, for DOE, and other commercial entities. And finally, he has many peer-reviewed publications, many patents granted, and he has solely authored one book on the Intel Larrabee architecture. So welcome to Josh. And our last attendee who I wanted to introduce is Rob Aiken. And then Rob is our distinguished architect at Synopsys. He's part of the Office of Technology Strategy, where he's looking into things like AI, machine learning, security, next generation design methodology. Prior to Synopsys, he worked at ARM. He was a fellow at ARM and has a number of patents, actually 50 US patents, has published over 100 technical papers on a wide range of topics. He's worked on 15 plus Moore's Law nodes. I'm afraid to calculate that number for myself, but I'm impressed that he knows that. And then prior to ARM, he worked at Artisan, Agilent, HP, and his PhD is from McGill University in Canada. So thank you to all the panelists. Again, I'm honored and thrilled to work together with this group. So what we're going to do now is we have each panelist is going to talk for about 5 minutes. They each have a couple slides to show. And then we'll go into some questions we put together, and then we'll go into audience questions after that. Okay. I'll hand it off to Dr. Carl McCants from DARPA.
Thank you, Ian. I appreciate the introduction. It's an honor to be here and definitely have many things to say. I'll try to be brief. Next slide, please. So when we think about microsystems and in particular where things are going, and part of how we at DARPA are envisioning the future, this chart shows a comparison of where we are today in terms of 2D or 2.5D, pretty much monolithic integration, primarily using silicon. If you think about some of the larger GPUs and some of the other CPUs that are being built, and more importantly, that the considerations of packaging are happening after fabrication. Where we see things going in the future is 3D with dense interconnects, disaggregation. We already are moving towards chiplets and that type of ecosystem. But more importantly, when it comes to the H in 3D-HI, it's multi-process and multi-material. And then kind of the final point is that packaging is no longer distinct. And what I mean by that is that we're really looking at how does the design of the microsystem itself, so the design, the architecture, now impact how this particular microsystem must communicate with the outside world. So you're thinking about how this will be, packaged, assembled, tested from the concept of the new microsystem. Next chart, please. So what do we think is necessary for a heterogeneous 3D integration? So the first is multi-chip, multi-technology assembly and packaging. It's one thing when you understand fairly well a silicon-based system. It's a completely different thing when you're throwing in compound semiconductors, wide bandgap semiconductors. You're having to deal with not only just crystalline mismatches, but also thermal and electrical mismatches. I'll go into that in a couple minutes. The second piece, the tools necessary for design, simulation, and test. And as we're looking to stack things on top of each other, now you have to start thinking a little bit more about not just bulk physics, but what happens at these interfaces and how you manage both from a thermal, electrical, and a physical stress at those interfaces. There's security. And so stacking things in 3 dimensions now opens up some opportunities for different ways of implementing security on these new microsystems. So again, an area of research. 3DHI interconnects. So when you're combining and trying to do the dense interconnections, when you're also thinking about, I'm now crossing some very interesting heterogeneous boundaries, how do I do that effectively so that I am looking at this kind of triumvirate of signal and power and managing all those different parameters? And last but certainly not least, thermal management and power delivery. Again, how do I get the heat out? What do I need to do to ensure that I'm dealing with things so that I don't cause issues in one material that's different from the next one? And that's my quick introduction. And back to you, Ian. Thank you very much.
Excellent. Thank you very much, Carl. Okay, and now we will go to, forgive me, I'm having a little trouble moving, to Josh Fryman. I'll show his picture a little longer since I missed it the last time. And hand it off to you, Josh.
Hey, Ian. So I'm going to amplify a little bit on what Carl was saying, but before I do, if we go to the first slide, I'd like to talk about when we consider next generation microelectronics, we have learned over decades many aspects to compute, whether it's CPU, GPU, AI, compute in memory, compute somewhere else. And there's a hierarchy that naturally evolves between where the compute takes place and then what you might have in the way of features to that. But there's another way of looking at this. If you go forward one, we can think about orders of magnitude that exist in the different critical metrics of how we use compute. What is my bandwidth per core computing element? What is my energy of operation? What is the latency that I have to sustain and be able to hide in the compute path? And the thing that I want people to stop and reflect on is when we talk about 2D, 3D, other kinds of materials and integration, many people will use brute force techniques within these orders of magnitudes, but it's actually the crossings between the orders of magnitude, if you go forward one animation, that present the opportunities. And when you're seeing more and more specialization of architectures and features and memories and interconnects, what I want to put on this piece of silicon versus this other piece of silicon, or maybe it's not even silicon, and put those together to get more advantage, the natural place to focus is where you have these orders of magnitude difference. This is actually going to drive a lot of how I think about and how I believe the industry is going to be thinking about 3D going forward. So to go to the next slide, to start with, we know that the economics of scaling and advanced factory nodes, we have cores, we have nearby cache, we have larger caches, but for economic reasons, we may not want to put all those in the same node. We may want to have those in separate physical nodes. So the natural thing you can do is you can build pancake stacks. You can have some generation N-1, N-2 memories, put on top of that the most current generation in logic fabrication of compute elements, and I can build a construct that looks like this, but now I have a lot of really fundamental challenges. And this is a 3D stack that you could do today, but I have I/O problems, I have power and ground problems, I have big thermal stresses that come out of this. And how can I do this in a way that yields and is very cost effective? What I'd like to suggest is that I can think differently. If I rotate this onto the side, I can go back to that pyramid and think about the natural tapering effects that exist and where I need to get bandwidth to different levels of compute or memory hierarchies. So I can now think about using the edges, and I can bring in a bottom layer, which is my legacy I/O interfaces. And these ports are my PCIe ports, my memory ports, things of that nature for large legacy interfaces. But I can also exploit the higher edge connectivity and bandwidth to put memory directly on top of my compute instead of having it outside of the package. I can bring large capacity, high bandwidth memory into the package. I can now get extreme I/O bandwidth into it without doing very expensive wire walks to the edges. But now that leaves the question of how to get power and ground through this. I can start thinking about running it laterally, horizontally through this stack in terms of power and ground. If you go out one more, Ian, that the power and ground can now run through there, but that leaves me the other two faces where I can now add future I/O, something like photonics or RF or other materials. The challenge with this picture is, even though I believe this is the direction we'll be going over the next 15 to 20 years, if you build up the last step here, there is a plethora of hard challenges that need to be solved. You can apply AI techniques to try and optimize many things, but AI is not going to come up with innovations such as rotating these dies different directions. We have no language. We have no assembly design kit or ADK equivalent to reason about die orientations, how I want to connect them, what my materials are, on top of the fundamental challenges of actually making something that looks like this. Where are the tools? How long does it take on the tools? We've talked, Carl said security. I worry about a different kind of security. How do you trust this assembly? How do you know there's not a man in the middle attack somewhere in this assembly? Right? How do you deal with the cooling and the disparate materials? If I bring in something non-silicon into this for an RF or an optical layer, am I going to have thermal stresses that break and cause the entire unit to fail? So we also have the EDA and the design methodologies. So there are a huge amount of problems here, but this is the direction that I think that we should be going based on many decades of analysis of computing. That's my introduction. Back to you, Ian.
Great, thank you, Josh. Appreciate it. This is awesome. Let me go on to think through Intel, and now I'll introduce Rob Aiken and his introduction. So, Rob, what do you imagine the future will look like?
Sounds good. Well, thank you, Ian. The advantage of going last is that everyone else has already said some important things. So I agree with them. Those are good things and important. How are we going to build these systems? I thought it would be useful to show for this topic two things. Number one, here's a kind of a canonical 3D heterogeneous system. So in aerospace and government, that might look like having an antenna array, passive antenna array sitting on the top, followed by an RF transceiver in a compound, semiconductor, then you've got filters, digitization, processing, interposers, all stacked up. And this is the vision of the future that we're looking for. But there are a few steps to go to get there. So if we look at where we're at now, it's somewhere between 2.5D and 3D, depending on who's building it and what they're building it for. And part of the challenge that we see going forward is how are we going to get from here to there? And even moving to 3D adds a whole bunch of challenges like we've talked about already with security, with thermal, and with signal crossing, ESD, you name it. But moving to the next step with different materials adds a whole new layer of complexity. And that's kind of what I wanted to talk about as well, is going right down to the guts of this stuff. So in addition to the interfaces that Josh was talking about, there are also material interfaces that are critical. And we need to be able to analyze those. We need to be able to see what happens, not just what are the complexities involved in building them, but how do they behave over time? And then when you take the wafers manufactured from one process to another and you start connecting them, now you've got different thermal coefficients, so they expand and contract differently. All of this stuff is physics and all of it can be modeled at some level. So it's important to have tools that are able to do that. We then have to integrate all of this learning from these lower levels into the higher levels. So we want to live in a world where the person designing that system and on the previous page doesn't have to worry about what exactly happens when you connect a 3.5 wafer to a CMOS wafer. That they should just be able to design in a system where the tools take care of that, the design kits that they have take care of that, and so on. It's great if we could have somebody who knew everything about how to build a system software down to how to do fundamental atomic structures, but we don't really need to live in such a world if we can abstract those up as we move along and have a tool chain that supports that. So really, again, in addition to what we've talked about so far, I think from a design technology or system technology co-optimization standpoint, we really want to be able to have enough of an abstraction of these various layers that we can make informed decisions about how we put them together and come up with our systems based on not just hoping that these things will work, but on knowing that they will work because somebody has done the pre-work to make sure that they can. So really, I think getting all that going is really a key function of the ecosystem. It's something where government and industry working together with academia can collectively resolve some of these problems and get to the state where, again, we can design these 3D HI systems from the get-go. Thanks, Ian.
Very good. Thank you, Rob. Okay, now we'll go ahead and jump into some of the questions. And if the panelists, let me start my video. We should all, Josh and Carl, if you wouldn't mind starting your videos up. All right, so the question I have, and this is for all of the members of the panel, how will 3D HI involve in aerospace and defense? And does this align with your expectations for commercial? How are they different? I'm looking at Rob. So Rob, why don't you start? You can keep talking.
Sure. I think there's a fundamental difference in how aerospace and defense is going to approach this compared to commercial. So commercial is very focused on high performance digital, getting these memory systems connected to each other, building the kinds of things like Josh was talking about or other structures. That's going to evolve. That's already in progress. It's going to do things, but the addition of the other types of semiconductors, the mixed signal designs, the RF, photonics will probably be in both, but RF is more likely to live in aerospace and defense than it is in commercial. So all of this more complicated world, I think, is really the distinction between A&D and commercial.
Okay,
if I
thank you.
Piggyback on what
Carl.
Rob was just saying, looking at some of the exemplar microsystems from NGMM phase 0, where you do have, again, phased array, so RF technology, as well as focal plane arrays, things that, again, with regard to the defense market, or just say national security market, those are some specific applications and capabilities, because one of the things we like to talk about is what are some of the capabilities that we will need moving forward. And that's an opportunity space moving forward that I think will probably be more aligned with the defense side. I think there is overlap with the commercial side, again, because when you start talking about computing, high-speed computing, those needs, sure, the faster I can collect, analyze information from a suite of sensors that I have going, again, that decreases the time from information to intelligence to move forward.
So I guess
Excellent.
I would agree with these comments. The wrinkle that I would maybe push back a little bit on is that when we talk about commercial space, to level set, hundreds of millions of units easily every year. And when we talk about aerospace and defense, we're talking about very small numbers, right? Maybe tens of thousands. And there's a distinct difference that emerges when we think about large, high volume manufacturing versus the lower volume manufacturing and how I think about 3D HI. I think A&D will advance commercial space and the 3D HI integration strategy for these reasons, but it's going to remain a very expensive, low volume part. However, it's a great test bed to develop the capabilities and techniques. Pushing back a little against Rob, I do agree with the things you were saying, but we actually do a lot of non-digital work. in standard client and high-end compute now. And yes, photonics is part of it, but we're also looking at RF for other reasons, because there is a limit to electrical scaling with classical IOs like PCIe or CXL interfaces. We need a different physical layer to drive 10 terabytes per second off the socket of bandwidth, because you can't do it with a high-speed SerDes kind of interface. You need something different, and RF is one of those candidates, as are photonics. So I think the challenges do exist in commercial space. I think they're going to lag behind where A&D is pushing to go faster, and I think A&D will pioneer the capabilities, but I think everything we're talking about does wind up in the commercial space. With that caveat, it has to be economically reasonable at hundreds of millions of units a year at 99% yield.
Yeah, absolutely. I think automotive is an area where you might actually see the transition from the A&D, everything's a prototype, some universe, into the high volume. I want to build 1 billion of these things. And that's I think an angle where, again, there's a strong need for, especially processing radar signals or processing RF, just processing a huge amount of information, feeding it to some kind of AI accelerator, and then doing something with whatever pops out the other side. So I think the RF challenge is, I think, different in the data center than it's going to be in an airplane, because effectively just the scale is different and the environment is different. So even if they are using similar technologies, they'll be using them differently.
The environment comment, I would definitely double down on and say that data centers and even cars and homes are extremely benign environments compared to the A&D sectors, right?
Yes.
You're talking about high altitude commercial aircraft, you're talking about low Earth orbit satellites. Those are very different requirements.
Absolutely.
Okay, very good. Thank you. Let's go on to our second question, which is related. Actually, as you talk about millions or hundreds of millions of units, or even 10,000, how do you decide, when do we get to 3D HI, which reaches production? And what are the barriers and challenges to reach production? I think, Josh, you had a nice slide that started that out. So why don't you go ahead and kick it off for us?
I would actually argue, and Rob and Carl and Ian, all feel free to throw rotten tomatoes at me. We're already doing it, right? But we're doing it very specialized and very low volume. In the industry, we call it ultra low volume because it's just that small, right? It's a rounding error somewhere down in another rounding error. But we are doing this at some level. What I was describing in my vision of where I think we'll be in 15 to 20 years is where I think large volume mainstream applications will exist. I think there's a huge set of challenges to get there, because the 3D HI we're doing now is 2 or 3 layers. It's not hundreds and thousands of layers at different rotations and interface boundaries and multiple kinds of materials and all the issues that come with that. My hope, right, not to pat Carl on the back for a good job or anything, but my hope is that NGMM is successful at getting a 10-year product shift left, a 15-year research shift left to make it go a lot faster. But if things like NGMM don't work, I don't expect to see the kinds of things I was showing before 2030. Sorry, 2040, 10 years past.
Sure. Carl, what do you think?
I would agree with Josh. We're currently, again, even for specialized products, there are companies that are doing the heterogeneous part where they are integrating, hey, here's silicon with 2 6s or 3 5s, but those are specialized components for a particular application. One of the things that we're trying to do, again, is open the aperture, and as both Robin and Josh have described, you need the infrastructure or the ecosystem where you've got the ADKs, you've got the ability to say, okay, well, actually what makes sense to put on top of what, to put in what orientation, to do all that. That's part of what needs to be developed. And so, one of the goals of the NGMM program is to kind of pull that, and let's see where we are after 5 years, to basically, do we have an alpha ADK, or is it a beta ADK, or have we set the right groundwork so that at least the initial investments and the initial capabilities that have been demonstrated can be picked up and then further developed. and to really, really, push the research, because one of the things in terms of moving forward really is expanding the research base so that the amount of understanding becomes more of an exponential increase as opposed to just linearly from, oh, we've got, 1Z, 2Z, 3Zs. Actually, we have a number of organizations, number of groups working on the same thing because they have the ability to test out their theories in a real place that says, okay, here's a correlation between the simulation and the actual result. And as Josh was talking about, you really have to start thinking about and looking at reliability and yields and how all of those things play into what you're doing with your design and architectures. Early again, DARPA is always trying to let's break the roadmap, let's pull things in, 2, 5, 10, 15 years so that the slope of the capability increase, changes dramatically.
Okay. And Rob, what do you think? Can the tools that you talked about make a difference with what they are surmising?
Yeah, for sure. And I think one of the advantages of playing in the tool space and in the IP space is that people contact you very early in the design cycle because they need you can't get very far if you don't have tools or IP. So we're hearing about a lot of things going on in 3D space. Some of them could be classified as 3D-HI. A smaller number could be classified as 3D-HI under Carl's strict definition of stop saying CMOS on CMOS. But the key part, I think, is the word. What do we mean by reaches production? Because in Josh's organization, it means a very different thing than it does in some of our organizations or some of the A&D type organizations. And that's, I think, where the difference lies in readiness, and why I think Josh is correct that the A&D sector is going to lead everyone else, because the definition of can I get enough of these things working to make this larger system work is good enough for production. Whereas can I make this thing economically viable and ship them in the hundreds of billions or millions and not lose boatloads of money? That's a completely different set of criteria for what production means. And so in between those two things, we'll see things reaching some definition of production relatively soon, but it's definitely things like the NGMM, I think, really do have, as both Josh and Carl have said, the potential to move the timeline forward in an important way, I think.
Okay, and Josh or Carl, I transitioned to question 3 because Rob was wonderfully pulled it right up. But what do you think about production ready? And Rob's had a few points. What does it look like in 3D-HI and in aerospace and defense? And maybe there's a difference with you, Josh, with you're talking, we're doing it today in low volume. What is that? How do we get to those steps of high volume production ready? Or what do you think?
So let me throw out a couple of comments. I'd actually really like to hear what Carl thinks on this question, because I think it's a wonderful landmine to step on.
Yes,
I think you're terrified to move. But let me come back to high volume manufacturing for a second. High volume manufacturing relies entirely on economy of scale. And the reason we get those yields is because we run a massive amount of wafers. The A&G sector, the A&D sector is not a significant number of wafers per year. So to get this production ready, right, I have to now put that in two contexts. For the very pricey, low volume, possibly at pretty good yields, but there's just not enough to drive economy of scale, or where I've made it extremely mature and I've driven the cost significantly down. So the capabilities of miniaturization, shorter wire walks, right, more energy efficiency, right, all those swap C issues come into play. I have to run more material. But let me take a step back. We've been talking about physical tooling. There's a whole nother business side of this conversation for production ready, which is, Intel does high-end logic. Other makers do 3, 5, 2, 6, whatever the other materials are. When you bring those together, you have to share a certain level of IP knowledge about where the ports are, how they're connecting, what the requirements are for the physical assembly, the ADK, the assembly design kit. Now you have a whole new business problem of, well, am I going to inadvertently leak my IP to them or their IP to us? Will be cross-contaminating, or is it the genetically modified food crops that now they're pollinating things around them. Who owns this, right? So you also have a lot of other issues, not just the pure mechanical, technical scientist. Can I physically put this together and make it work? We'll figure that out. But there's a whole raft of other issues that come with production ready. And then what does production ready mean to a customer? Some customers buy 10,000 units a year and they're happy to pay $100,000 a unit. Some customers want $10 a unit. Right? So production ready means different things to different users.
And if I could take up on what Josh was saying, I think one of the other challenges is it possible to move that line so that the quality levels and the reliability levels at what are considered typical aerospace and defense volumes are closer to those of the higher commercial volumes, so that you begin to at least address some of the cost issue? Because I think what's happening more and more on the A&D side is that a lot of attention is being paid, to cost, and are there ways to reduce those costs? You're absolutely right, Josh. There are certain applications where folks say, I don't care, so much about the cost. This needs to work. It needs to work for X amount of time. I'm looking for a reliability of X. I'm looking for performance of Y. And if you can get it to me, I will pay a premium for that, because that's what I need to have. Conversely, I wonder if there are potential technical solutions to driving that higher cost down towards what is, so instead of $100,000, you may not get to the $10, but if you could get to $1,000 or $10,000, that's a win both sides. And that potentially opens up the door for utilizing some of the high volume techniques and processes on the A&D side.
I think there's two extensions to that are important. So one of them is just the standardization of assembly design kits and so on, like Josh is talking about, and that's something that we've been working on. But I think there's another piece that's really important for both reliability and yield in this space, is you're going to have onboard test capability and potentially onboard error correction capability in order to deal with these interfaces that are going to, no matter how good they are at time zero, they're going to have some reliability issues. And I think the devices themselves are going to be able to need to work around those. And that's of course application dependent as to both how important that is and how feasible it is. So in some applications, if your high speed object is able to reconfigure itself so that it's operating at essentially full capacity, but it's now got a slightly different wiring than it had before, that's terrific. That's basically what happens now in most digital systems. But in some of these other ones, you might actually want to have more of an onboard tuning that just says this device has started out here, it's now gone there, digital part, here's the new world, accommodate it. And that type of reliability monitoring and on the fly reconfiguring, I think is probably going to be necessary to make some of these multi-layer stacks work. And that will also help them to get into production at earlier stages.
Yeah, very good. So I have a number of questions, as you all know. I'm going to skip a couple because I think I want to get to the point where we can do some audience questions. And this is very good, by the way. This is excellent. Enjoying the talk and the great dynamic. So we're going to skip question 4. We're going to go to question 5. And this actually aligns a little bit with some of the audience questions that are out there. Looking at what are the differences between 2.5D, 3D, and then 3D HI. And then, let's pull into the pieces that are somewhat EDA specific, the design, the verification, the prototyping, the manufacturing. Okay, now we just got out of EDA. But also in the use in the ecosystem. So maybe pre-silicon, post-silicon, and even the pieces. You look at a design like what Josh showed, or even the multi-layer ones we have of today. What ecosystem elements might be important to making this capable? And I will say, let's start off with Carl, if you will, and then we'll go on to Josh.
Okay. So I think if you look at what we currently can do today, and I'll use an example from Josh's company, the Panevecchio chip, where that's again clearly here's a 2.5D design, a number of different CMOS technology nodes, intricate interconnections, the ability to actually not just design, but all the steps that you just mentioned in terms of the prototyping, the manufacturing. Hey, this is now a product, and how did we get there? And as both my colleagues have pointed out, if now I move from silicon to something else, whether it's 2.5D or 3D HI, and I'm using let's say a focal plane array where I have mercury cadmium telluride as my photosensitive layer. Okay, so now I have to look at the interface between the mercad tel and the silicon readout integrated circuit that's immediately beneath it. So that changes then how I do my verification and how I do the prototyping, because the first question is this going to be a cooled FPA? Is this going to be room temp? So again, gallium arsenide versus mercad tel. How do I do this? Then the other pieces of that ecosystem now come into play in terms of how I have to think about that, and coupled with what both my colleagues have pointed out over and over, and that is the volume differences and the planned end use of those, which then says, hey, what is the customer willing to pay for these parts of that ecosystem? So that's kind of where it is. And again, just to emphasize something else that Josh mentioned, and that is that there are companies that are currently doing what I just described. Hey, here's a cooled IR sensor using 3D HI. Is there the ability to readily get access to that? Is the cycle time for going from, hey, here's an idea of if I'm a grad student, let's say at UCSB or USC or MIT or Purdue, I can't, I don't have that access. And so that's kind of one of the pieces. And in terms of the differences, I think that is a subtle but important difference between A&D and commercial.
Excellent, thank you.
I would agree with everything Carl was saying. I would actually suggest not changing anything, but just expanding on it. The diagrams I show, they're very futuristic. We're obviously not doing that tomorrow, right? And I'm frequently called crazy for good reason. But if you take one step back and you think about this, right, the reason I'm making the argument is that we can do pancake tower stacks, sure, but there's a limit to how you can get those connections through there. You wind up with these serial dependencies, which deeply impacts yield. You need tighter and tighter pitch of the bonds and the vias. And you now have an issue that you're moving logic and operations between these pancake towers. So when you look at any individual wafer, how do you test it and know that it works when it represents fractions of functioning units?
Right.
The test vector problem becomes very different. So you almost get to a point where you do very minimal short testing, you stack these things up, and now you do blind build testing and trying to characterize it. The side effect of that is we all know that's terrible, right? The yield of that is going to be zero. So that means back on the EDA side, back to the architect who's thinking about what they're trying to do, you have to design in redundancy and resiliency and what I call graceful degradation. Because of aging effects, you're going to burn out some oxides, you're going to burn out some devices. You have to compartmentalize the design, not just chiplets, but within the chiplets, compartmentalize the design enough that when individual regions fail or become unreliable, you have a strategy to work around it in software and hardware. That means dynamic adaptation. We don't have the design languages to do any of what I just described. We don't have the physical tools for test, assort, edge CMP and assembly and bonding and quilting or stacking and rotating. They don't exist. There is a huge amount of research out there that needs to be done. Low volume, carefully selected pancake stacks we can do now with all kinds of crazy materials. The really advanced integration, we have big gaps in the entire ecosystem.
That's why I was
Okay.
pushing for some kind of on-die monitoring and reconfiguration and test, because I don't think there's any way to solve it. That problem that you just described, I don't think can be solved at T0. I think it has to be solved as well as you can at T0, but on the fly, graceful degradation, monitoring, etc. There's one problem that I thought I would add to this mix, where the existing 3D system that's in production is imaging systems. And they have an architectural benefit that allows them to get around a bunch of the problems that we just described. Number one is all the information comes in vertically. It then transitions into the rest of the system. And it's inherently a problem that you can work around. If your camera has a bad pixel, you can deal with it in software.
True.
Okay, very good. Now I'm going to skip to one question, or maybe one multi-part question, to focus specifically on NGMM, and then we'll go to some audience questions. Carl, let's start with you on this one, which is, the draft is available for NGMM. But can you tell us a little bit more about the intent of the NGMM program, and maybe a little bit about how that relates to things like EDA, IP, AI, et cetera? What are you looking for out of this program, and what are you looking to do and accomplish?
Okay, very simply, it's to create a center where you can actually do this 3D HI package assembly testing in a domestic location where we've developed at least rudimentary assembly design kits, and you can pull all these things together. We want to go from just here's a onesie twosie prototype to here's what would be considered, quote unquote, at least I'll call it approaching pilot line quality relative to what is currently done, commercially. And so it's working with folks who have expertise and understanding. I mean, the EDA tools are a critical part of this, but then so is the tooling that will be needed if you're talking about, wafer to wafer, die to wafer, how are we going to do this? We've talked about how we change the interconnect density. So there are specific, issues and advances that need to take place there. I mean, what Josh described earlier, there's a ton of research that needs to be done, but that's a part of what we are looking to do with NGMM. Let's again do some of the fundamental implied research necessary to get us to that point where, if I'm a grad student, I have an idea for what may seem to be a crazy stack structure, I could actually get it done. Much like if I'm a student over in the EU and I've got an idea for a monolithic device, I can send it to IMEC and bang, it comes out, and I get to test it and again do the comparative analysis between this is what was predicted by the modeling simulation, this is what I actually got, and can you move forward? One of the main points with NGMM is not so much, yes, having a domestic center for doing the 3D HI is important, but really it's more what gets enabled by that, the additional research, and then the sharing of the tools and the techniques with the US ecosystem. And as has been mentioned before, if, with I'll say A&D leading in that space, then sure, I think there will be tools, there will be learnings that apply directly to Intel and other domestic companies. And I think that's where the mutual benefit is. We've talked about, yes, transitioning NGMM, at the end of the program to the National Advanced Packaging Manufacturing Program, for that purpose. But it's not just, hey, you're going to have this, but the learning, I think, that gets dispersed within the domestic ecosystem is as important, as critical as the success of the program itself.
Okay, very good. And I think what we'll do is we'll go on to some audience questions, given we're at the 10:50 point of things. But the first question I wanted to bring up was this one, which is, how does DARPA, NGMM, and 3HI, these two efforts, how do they connect with other DoD and the broader CHIPS programs, and things like the, CHIPS and Science Act programs, like the NSTC, like ME Commons, and others?
I have a slide that describes this, and I'll say this, and I unfortunately have to run to another meeting. But let's. Can you pull that up for me, Ian?
I will. Yeah, hang on. Let me.
Not a problem. I think
minutes, if you will.
I'll keep talking. I'm somewhat good at filling in. One of the key things to I'll remind the audience is that DARPA's mission, again, we're looking out, and as I said earlier, trying to, in particular, break some roadmaps. That's I like the river there, and so where we see, and again, this is, since we're supposed to be doing that crazy high risk, high return R&D. So this is kind of a plot, so the y-axis shows the type of integration: 2D, 2.5D, 3D, 3D HI. And then the x-axis is a time to technology implementation. And so you look at the different programs, and I'll just focus on NSTC and NAPMP in the purple, the commerce efforts, and really looking at domestic fabrication and packaging. Okay, let's provide that capability. The Microelectronics Commons, again, extend that out a little bit. So emerging prototyping, workforce development, looking at a nationwide collection of capabilities that is, again, more focused on the defense market, so that there's that separation between NSTC and the ME Commons. What we're really trying to do with NGMM is to laser focus on the 3D HI and the H being the important part. And we recognize that there's a significant amount of manufacturing science that's needed to make this come to pass. So we're looking at things as I described before. How do you change the interconnect density? How do we address the multi-physics modeling for the different interfaces for addressing simultaneously, heat removal, power and signal delivery, mechanical stresses that are going to be present? How do we throw in security? How do we deal with a number of the other things that have already been described that are going to be critical to doing this? But again, the major focus is that this is, again, the laser focus on the H and the 3D HI, and what are the specific things needed to do that. So yes, the time to implementation is a little bit farther out than some of the efforts that are happening right now.
Okay. And what I wanted to do, maybe just step back a little bit. There's a question early on that just says, what's the difference between 2D and 3D? And to make sure that in our audience we're all familiar. And when we're looking at microelectronics, 2D is literally chips in a planar design. So you might have multiple chips, but you all have it in one plane, sitting on a substrate in a package. 3D is when you start to stack some of those devices, that the integrated circuits up, and you might have heard the term chiplet. And then when you go to 3D HI, it's when you start saying, okay, not only do I have silicon, but I also maybe I have a 3-5 material that does analog processing or RF processing, or maybe it's some other different type of material. I think Carl mentioned earlier talking about mercury cadmium type applications, and there's just a number of materials, and of course those things have different thermal properties, they have different mechanical properties, and how do those pieces fit together? That's why this is such a challenge. Moving on from there, what I thought I'd do is then drop into the next question, which was, can you give some use cases, and this is commercial and weapon systems use cases, for 3D HI? And why don't we start with Josh?
Sure. It's a great example I think Rob gave earlier about imaging, and Sony has been extremely successful with building high-end image sensors. And what they do is they take the image sensor array, they thin that die down, they back it up with additional processing and DRAM layers. And in fact, on your cell phones and your high-end DSLRs, when you take video, you have a choice of frame rate. And as you increase the frame rate, the resolution comes down. The reason is not because the image sensor can't do it. It's because you get a bottleneck, which is you can't get enough bandwidth into the DRAM for the buffer of the images. So as you increase the frame rate, you have to cut down the pixels to fit the little narrow channel. One of the advantages of going through 3D HI is that I can start to bring those directly underneath the memory technologies. I can get a much higher bandwidth down, but then you take a step back and say, okay, it's great that we're taking all this video, but as you've seen, the latest, high-end cell phones, some of the very high-end studio equipment for film and other scenarios, it's got built-in image stabilization, AI, HDR effects, compression, everything else. Again, you don't want to take that and then shove it across a horizontal link because you have all the expensive wire walks, the power, the complexity. If I could take neuromorphic or AI kinds of compute and stick it directly underneath that memory, I can now flow straight down. I'm moving microns. I'm not moving centimeters. So there's a huge power difference right there. I can now attenuate the information because I've got the raw stream, I've done the compression, I've done the recognition, stabilization, all the different color correction techniques, and I come out the bottom with an attenuated, cleaned up signal, which is very reasonable to now transfer someplace else through another medium, typically a horizontal attach, Ethernet, optic, on package, on board, whatever it is. Obviously, we want to put more and more things into that package. We want to reduce the distances. That's a dramatic reduction in power, but we have those challenges around reliability and design artifacts, everything else. This same argument works in compute. It works in networking. It works in radar. Take away the image, exactly the same construct, HPC, AI, radar, RF, right? Whatever you want to think about, that's the advantage you get from doing this.
Yep. And one further comment beyond that, that it applies to the cell phone and it applies to these miscellaneous weapon systems, drones, and so on. If you make that nice and small, then that expands the applications that it has. So the fact that your cell phone camera is small means that it can fit in a nice form factor and you can have multiple of them. If you can take a system that in 2D world would be big and make it physically small and lightweight, then it has all kinds of applications that it wouldn't have otherwise. So I think, like what Josh was saying, and that these are primary drivers for the applications.
Okay, I think we're going to go with one more question and then we'll wrap it up. But just for the folks who did ask some questions, if your name is in there, we will respond to you with some answers after the fact. This last question is: Will more thorough wafer tests to ensure known good die and more extensive built-in redundancy be required to ensure reliability for A&D application? I know we've talked about that a little bit, but let's just expand on that a little bit more. And let's start with you, Rob.
The answer is absolutely. The challenge, of course, is that known good die are not really known good die. They're known mostly good die. And in a 3D world where you have vertical interfaces that are not going to be, they're not going to be high-speed SerDes. They're most likely going to look basically like wires. There are various DFT approaches that you can use to do that, but every single one of them has some piece of wire somewhere that is not tested, because you can't physically contact all those things during probe. So you're using effectively a scan chain to look at them and gauge, are all the drivers to this thing working, or if I drive some signal here, is a receiver working? So you get known mostly good die, and the trade-off between mostly good and the amount of circuitry that you need to put on the wafer to accommodate that is one that I think is going to require a little bit of experimentation before we all finally agree that this is the right way to do it.
Okay, that's fair. Josh, do you want to close out?
I would double down on that, but I would also take this opportunity to maybe do a little campaign education for a second. I agree entirely with what Rob said, but I want people to realize we're talking about building wafers with sub 2 nanometer feature sizes. Yeah. There is no probe that will touch that and not destroy it. We're already at a point where we manufacture the wafer, we manufacture a sacrificial layer for probes to land on and then remove the layer when that probing is done. The second thing is, when you're doing quick sort and test on a wafer, you cannot transfer significant power into that wafer. So you're compromised in your physical area of what you can test, you're compromised in the level of power and the time at which you can be on the tool for the test. Completely agree with Rob, you miss huge things. You also miss the fact that in these big stack ups, you've got drivers for the vias you cannot test easily. So yes, always more tests, better yield rates, critical for volume and cost. When we get into these advanced designs, that's what we're talking about, designing in for redundancy and failures, because you don't have any other choices. There are no other tools in the toolbox.
Okay, very good. I want to thank all the panel members, especially excellent to have you, and great discussion. And I will now hand it off back to the NDIA team and ETI. So thank you, everyone in the audience, for attending. It's been our pleasure.
Great. Thanks so much, Ian. And thank you to all of our panelists and all of our attendees for a great event. What a great discussion. And thanks for all the questions. Unfortunately, we were only able to get to a handful of them, but we'll try and get some answers out, like Ian said, for those that were named. We are going to post the recording of this event online as soon as possible. But if you have feedback about this event or other webinars, other ETI events, especially topics that you'd like to see us cover in the future, please email us at eti@ndia.org. I also just wanted to take one moment to highlight some of our recent papers, upcoming papers, and upcoming events. You can find all of this information on our website, emergingtechnologiesinstitute.org. We just recently released a report. It was a workshop summary focused on minority serving institutions. And we have a number of reports that'll be coming out this fall, winter, and into the new year. We'll have one on microelectronics, another in November on joint warfighting concept. And then in early 2024, we'll be releasing the next report in our emerging technologies supply chain series. And that's going to be focused on directed energy weapons. On the event side of things, we have 2 events coming up in December. One will be co-hosting with the Hudson Institute, and that'll focus on interoperability. That'll be December 11th. And then on December 5th, we're going to have the next in our Tech 101 series, and that'll be focused on high-powered microwaves. So continuing in the directed energy topic. Like I said, all of this information is available on our website. You can also sign up for our mailing list to receive regular updates. So I'd just like to thank again Synopsys for sponsoring today's webinar. Thank Ian and all of our panelists today for a great event. Thank you to all of our attendees, and I hope everyone has a wonderful day.
Awesome. Thank you all. Cheers.